By that time, yeah, it's gonna be like a crowd. You know what? You were right. Well,
I don't know.
Okay, let's get started. I want to point out that we are midway through the semester, or a little bit over halfway. Some of you are doing really good with participation. Some of you, I did not hear your voice not once. So 30 points, participation. These can change grade from a B minus to a B, from a D plus to a C minus, so you can graduate. So easy points. I want to hear you. Ask a question. Answer, even if it's wrong. It's okay. It's all about speaking and talking and be part of the class and part of the engagement. Last week we gave the plus 10 to whoever was here on Friday. That doesn't mean you got the plus 10, just don't show up anymore to class. Still, participation in the class, being there, is all part of your engagement in this class. I know you don't need to be here. You don't have to. You're adults. You can make that decision. But if you're here, that would be good for participation, for engagement. All right. Atomic absorption and emission spectroscopy. So, in atomic spectroscopy, we have two categories. We have the atomic absorption spectroscopy, and we have the atomic emission spectroscopy. So, one based on absorption, obviously, and one based on emission of light. So, under atomic absorption, we have the flame atomic absorption spectroscopy, which you've been doing in the lab, except for one more group on Wednesday. And the electrothermal atomic absorption spectroscopy is another form, another instrument to do atomic absorption, but we don't have that here. But I'll talk about it briefly today. So, at the emission, there is flame emission. It's not very commonly used. It's used for select elements like sodium and potassium. Those atoms or elements that ionize at low energy, so can be determined by flame emission spectroscopy. But the most common technique, or more common technique, is the inductively coupled plasma atomic emission spectroscopy. So it's gaining, gaining prominence. It's becoming more used, and it's mostly, we don't have one here in food science. It can be used in analytical labs such as Medallion Lab and Covan's Lab for analysis. They have an ICP for elements analysis. Also the Soil Lab here in the University of Minnesota, they have an ICP for determining minerals in soil. And then what's the main application for atomic spectroscopy is mineral nutrient analysis, like we did in the lab. The two minerals that we did were calcium and iron. They are listed on nutrition label. That's why we analyze them. But there are other nutrients, or we call them essential nutrients, that we need to ensure that they're there, and the content of them to meet a particular daily value. And another thing that we need to watch out for are the toxic elements, or the heavy metals. So looking at your periodic table, all those that are in pink can be measured using atomic absorption or atomic emission spectroscopy. We care for essential nutrients that we need them in micro and macro amounts, or nano amounts even. But these are listed here: calcium, phosphorus, potassium, sodium, chloride we need, that, iron, iodine, zinc, copper, manganese, and others. You find these in table 9.1 in your chapter 9. Toxic elements that we need to watch out for is lead, mercury, cadmium, nickel are toxic. Arsenic at a certain amount can be toxic as well. So the USDA database has a lot of these nutrients listed there with their needed amounts and the amounts present in different food products. So a lot of these elements, you can go back and look at the USDA website to determine the content in different food products. It's not complete, but they're there. If we look at atomic spectroscopy, transition of energy, so in absorption, we talked about it earlier, it's electronic energy, because if you're looking here at the absorption of light by a singular atom, not a molecule, okay? So all the energy type that is absorbed by an atom is electronic energy, and that is the energy that the electron absorbs and it moves to the excited state to a higher energy level or a shell. So the valence electron moves to an upper shell. That is when it absorbs, and then when it emits light, what happens is some of the energy is dissipated as heat, and the rest of the energy is emitted as light. And that's what you can measure as well, emission of that light or that energy. So this happens for atomic absorption, it happens at the UV vis range, and that's where the electronic energy is allowable. And then when we say atomic, the atom should be neutral, not ionized, and in the gaseous state. So in atomic absorption, we make sure that our molecular bonds are broken, and then the atoms are in the gaseous state, and then that's when we measure absorption or emission. It won't be at the ionized state. So typically, every element has a spectra, or it absorbs light at a specific wavelength. So you can monitor absorption for different elements, and also you can measure emission or monitor emission of light. You can see here, like we said earlier, that the emission happens at a longer wavelength because you have lower energy associated with the emitted light. Absorption happens at higher energy, shorter wavelength. So, okay, absorption occurs as the atom goes from ground state to excited state, and then it is again electronic energy. We do not have vibrational or rotational in an atom because you don't have molecules, so there is no bonding, so you don't have stretching or bending of bonds. Alex? Oh, not Alex, Zach?
Why aren't like all elements able to be measured by atomic absorption?
Good question. Why not? Some of them do not absorb light, basically. If they don't absorb light, then you won't be able to measure them. They can be excited. Okay. So back to here, we don't have vibration or rotation since it is a singular atom in the gaseous state. So it's only the energy level of the electronic energy level is what you see in that energy spectrum. So many of you have seen that already in the lab, so you're familiar with it. So your sample, first of all, is in liquid form. Your minerals are dissolved. So what you do is you, first you have a nebulizer where your sample is converted or is aspirated, and then fine mist is projected into your flame. Okay, so that is your first step, where you have your sample aspirated, and then in the use of nebulizer transforms into a fine mist, and then goes into a flame or plasma. So here your elements are still in a molecular form, but they are in small particulates that hit the flame. The solvent will be evaporated and bonds will be broken. So we have vaporization of your solvent, and then the bonds of your molecule or elemental molecule will be broken, and you would have singular atoms. So you will have your minerals as a molecule form in solution. We remove the solvent and then vaporize into the gaseous state in the flame, and then the heat from the flame causes the breakage of the bonds to get an atom, and then the atom gets the light from your lamp, and then it gets excited, and that's where you measure absorption or emission after going back to ground state. Or if the flame is too high or too high of a temperature, you can get your atom ionized in the ionized form. You don't want that to happen. That won't absorb light at the same wavelength. Then you would need to make sure that your flame is being adjusted to avoid any ionization and maximum absorption in the atom state. So, did I miss anything here? No. Okay. So you have the lab. The lab is the source of energy, source of excitation. So in atomic spectroscopy, you have a source of atomization and source of excitation. In atomic absorption, these are two different sources. Flame is a source for atomization, and your lab is the source of excitation. So the lab that you used in the lab is the hollow cathode lab, or some of you will still be doing that from one state. So that lab basically is filled with an inert gas, argon mostly, or it can be filled with neon. And you have an anode and you have a cathode. The anode is made up of tungsten, so this would give you the electrical energy. And then what you have, electromagnetic energy, and then what you have is the cathode, and the cathode is made up of the mineral metal that you are interested in measuring. So if you're measuring iron, so the cathode will be made up of the metal form of that iron. And if you're measuring calcium, that cathode will be made up of that metallic form of calcium. So the reason is that once the energy is given out, you would get the radiation that is emitted in the exact spectrum for that element. So all of the wavelength that would excite that element. So oftentimes you have to replace the lamp like you did in the lab. So you have a calcium lamp and an iron lamp. Sometimes you have a lamp with multiple cathodes that you can do multiple elements at the same time without having to change the lamp. Another type of radiation source is the electrode-less discharge lamp. That means you don't have an electrode in there. You have the discharge is produced by radio frequency generator coil, so you don't have electric current. Everything else is pretty much the same in that. So not much of a difference, except that the source of energy is the radio frequency generator coil rather than an electric current. These both are old now. We have a newer one. Right, Cindy? These are old. An older and an old, right? We have a different unit. So now we don't have either. We have a newer version. Yeah, we have a newer version. That is the very old one that when I came, this was there. And then we had a newer one.
So that was the newer one on the right?
Yeah, this one was the newer one.
Oh, okay.
And then now we have an even newer one. But basically, some of you've seen the atomic absorption unit already. You have the nebulizer, you have a tube, aspirating tube that you would put your sample and insert the tube in it. And the compartment here is where you have your flame. You need, of course, an oxygen source, and usually it's compressed air. And then you need a fuel, and it is acetylene. So you need fuel, you need oxygen so that you can light up the flame. And then your sample is aspirated, so you have your sample in here it's a flask or a beaker, whatever you have it in, or even in a plastic container. And then you insert your aspirating tube, and then the sample is aspirated into the nebulizer, and then is converted to a mist that goes into the flame. So you would have your flame here. And these are the controls that you use usually to adjust your air and fuel so that you have flame that is hot enough to atomize and not too hot to ionize. Because if the flame is cold, then you won't break all the bonds, so you will have large molecules in the flame. They will scatter light. And if they scatter light, less light is going to get to the detector, less transmitted light is going to get to the detector, and then the detector is going to assume that there has been high absorption, so it will overestimate your results. Overestimation. So that is question 4 of your lab report. You can say that if the flame is too cold, you have molecules in there that will scatter the light, and it will result in an overestimation. Okay. On the other hand, if the flame is too hot, then your atoms, you break the bonds, all right, and then you have the atoms, and the atoms will be converted to ions at high temperature. And these ions absorb at different wavelengths, so you will get underestimation. That is a reason for underestimation, one of many reasons for underestimation if your flame is too hot. But if you are an experienced analyst, you will know how to adjust your air and acetylene to avoid either cold or too hot of a flame. So basically, you have now your sample. So here's your tube inserted in your sample. It gets aspirated into the nebulizer, gets into a mist. Here's your flame. Here's the source of light or energy is your lamp with the appropriate cathode, so the incident beam. This is your sample holder. So that's your cuvette. Is your flame compartment or sample compartment. So your sample now, your atoms are in the flame, they get the light, they absorb light, and then the transmitted light goes to the detector. And then you measure absorption at a particular wavelength, and Beer's law is applied. So the energy is converted to electrical signal that gives you the absorption. The calculation is done so that the transmitted light is converted to absorption. So here's another animation to show you that after the light, the transmitted light, it goes into the detector. You have a monochromator where you select the wavelength at which you want to measure absorption. Because the light that is coming off from the lab have absorption at different wavelengths. So you have a spectra. So you want to select the wavelength at which you have maximum absorption. So that's why, even though that you have a cathode that gives you a specific spectra, the element absorbs light at different wavelengths. You want to select the wavelength at which you have maximum absorption to enhance your sensitivity. Okay? So you have your monochromator here that will get the light that is coming off of the flame, get diffracted, and then a singular wavelength is allowed to pass through into the detector. And then the detector you have in your atomic absorption unit is a photomultiplier tube. remind you, it's a multiplier detector. That means you have your energy that hits the anode. The anode here, the cathode here. The radiation hits the cathode emits an electron, and then it gets amplified multiple times until you have a lot of electrons that reaches the anode. So it amplifies the signal. So you have better sensitivity and lower threshold. Okay? And then from there, your absorption is red. Okay.
So in that today, we were talking about split width.
Yeah.
And like for calcium, I believe the split width is like set at 0.7. That would be 0.7 nanometers, correct?
Yeah.
Because it's
Yes, it's in nanometer. Yeah.
okay. And then for iron, it's like point something. I think it's much less.
Much less.
Is that because the peak? I'm looking at this liquid spectrum.
So much less. Can you remember what was the nanometer of the iron?
248
248. Okay.
and 422 for
422,
calcium.
248. Okay. The one thing I would say is you have sometimes spectral interference. You have elements that would absorb at very close wavelength. So if you have, let's say in this case is iron, and you have spectral interference very close to that singular wavelength, you try to narrow it as much as you can, and then you tend to lose on threshold, but then you make sure that there is no absorption from different elements. In calcium, if you don't have elements that absorb close to that wavelength, you don't worry. The more the slit, when you increase the length, maybe more than one wavelength can pass through, but it's okay. You still get sensitivity. You don't get spectral interference. So this varies between element to element, depending on what spectral interference is going to be around that wavelength that you're trying to measure. And also, you want to think about the slit width or influence the radiation power. Okay, how much light is getting, how much you can get energy, so that the more you have, the more sensitivity you can get. But if you have spectral interference, you have to narrow that so that you don't get spectral interference. Okay. The other form of atomic absorption is, instead of having a flame, you have a platform where you can heat it, a graphite platform. So this graphite platform is the source of heat, where it gets heated at really high temperature, and you actually place your sample on it. And then it gets heated at really high temperature, and that's when you get your molecules in a gaseous form, and then breaking down of the bond, and then you get your atoms in a gas form. So they evaporate up, and then the light is projected, and then your atoms in the gaseous state absorb light, and then you can measure absorption. Okay, so everything else is pretty much similar, except that you don't have a nebulizer here, and you can put a very small amount of sample. So if you remember, those of you that did the lab, you had at least 10 milliliter of a sample, and then you have to have that much sample because aspiration takes a lot of sample out. Some of it goes to the waste, some of it make it to the flame. So you need that much sample. For this, you can work with a drop of a sample. So you can have less of a sample if you have sample volume limitation. So you can accommodate smaller samples. It has lower threshold. Another difference, it's more expensive than the flame. So you don't see it in very many labs. And another issue with it is lower sample throughput. So here you have to put one sample at a time, and sometimes you have to wait until it's cool so that you can open it and put a sample in. Whereas in the flame atomic absorption, you don't need to worry about that. You have more, you can run through samples much quicker. So other issues with it is lower precision, matrix interference. So it's not very well favored for many of these reasons. Atomic emission spectroscopy. So here we're looking at emission of light. And we have two types. The one that is flame emission spectroscopy or flame photometry. So they both measure the emission with photometry. You use low flame temperature and then you have filters instead of monochromator units. You filters for filtering the wavelength. So it has the same system as an atomic absorption would have, but you are measuring the light that is emitted. And when atomization is required, so you still need to break your molecules into atoms in a gaseous state. But the difference here is you don't have a lamp. The heat is used for both atomization and excitation. So the heat that you generate is used for both, and because of that, only the elements that excite at lower energy are usually measured using flame emission spectroscopy or photometry. So these are sodium and potassium. They get excited at lower temperature, so you can measure those with flame emission spectroscopy. So ICP, so flame emission is kind of spectroscopy is phasing out, and then ICP is getting more use right now. So the ICP again is inductively coupled plasma atomic emission spectroscopy. It's called inductively coupled plasma because we are using plasma and we're using radio frequency applied to a copper coil to generate the energy to heat up an inert gas to generate a plasma, which is the fourth state of matter. So that is when the gas gets ionized, it becomes plasma. So it is the fourth state of matter. So argon gas is commonly used, and the argon gas, when it gets energy from radio frequency, it gets ionized. So you end up having high concentration of cations and electrons in the plasma. Can reach to really high temperature. Although it's really high temperature, you don't get ionization of your atom. So here you don't worry about too high of a temperature ionizing the atom because the argon or the ionized argon in the generating that plasma has a lot of ions itself, the cations and electrons. So it prevents ionization. The presence of that much of cations and electrons prevents the ionization of your atoms in the plasma. So you don't get ionization although the temperature is high. So again, you have your sample and then you have an aspirator that gets it, nebulizer that gets it into the flame. So you have the argon as a source of air, and then you have the copper coil and radio frequency applied to the copper coil, which generates high energy that ionizes the gas and generates the plasma at really high temperature. So, and then what you have here, you don't have lamp. There's no lamp because the plasma is the source of atomization and the excitation. So your atoms or your molecules that get into the plasma, they get atomized and then they get energized. So they get excited, and then after excitation, they go down to ground level, and then they emit light. The emitted light goes into your detector. So the spectrophotometer, you have a grating system so that you can diffract the light into the multiple wavelengths and select the wavelength that you want to measure absorption at. This is a system that has multiple photomultiplier tube detectors. So in this system, you don't have only one photomultiplier tube, you have have multiple. So you can actually measure elements simultaneously. So you might have one for iron, for zinc, for calcium, for potassium, for whatever. So you have here 1, 2, 3, 4, 5, 6, 7 detectors. So you can measure up to 7 elements simultaneously. Because then you can select the wavelength, and then each wavelength gets directed to a photomultiplier tube detector. So you can have sequential or simultaneous or charge injection detector. I'll talk about that in a second. So this is just showing where you have the coil, you have the radio frequency that gets applied to the coil, and then it heats up, and then you get the ignition of the plasma. So this is just a visual. Okay, sequential photomultiplier tube spectrometer. So here you have a system with only one photomultiplier tube, and then you can select to change the wavelength every so seconds. Then you can get a measurement for multiple elements. Instead of changing the lamp each time, you just change the program to select 4 different wavelengths and then sequentially get the absorption. Or like this, you have multiple photomultiplier tube detectors. This is more expensive, so this unit has multiple detectors, and then you can measure simultaneously multiple elements. Okay. Or you can have the Emission spectrometer. So the Emission is very expensive. It kind of works like a photodiode array detector. Obviously, different mechanics, different setup, but the idea is the same. You get a fingerprint. You get multiple wavelengths, and you get to measure multiple elements simultaneously. So what happens here is your light coming from the plasma is projected to a prism first, and then a grating system. So it gets diffracted into multiple wavelengths, and then projected into a charge injection device where you get absorption at multiple wavelengths. So you can detect a much larger number of elements than instruments with photomultiplier tube detector. So it is expensive unit, but much more efficient than just having a photomultiplier tube. Okay. So applications. So determining mineral content in food. So some of you in the lab already have started working with determining calcium and iron, and we have 2 mechanisms to get your elements to be ready for analysis by atomic absorption or atomic emission. So the one method we have used for your mineral analysis is dry ashing. So basically, we're going to cover this when we talk about mineral chapter in more detail, but just briefly here, you want to get rid of all of your organics. So you want to get rid of all of your carbon, nitrogen, sulfur components. So you put your sample at really high temperature in a furnace, and everything gets oxidized or burned off. What is left is the ash, and the ash contains your minerals. Okay, so that's what the sample prep prior to your lab is. Getting your food samples, ashing them. We call it dry ashing because you don't put them in acid. So you dry ash your sample, and then you wind up with your ash. Now sometimes your ash is dark. Still, when it's dark, it has more carbon still left in it. So what Cindy does is take it out of the furnace, add a little bit of nitric acid, kind of like combining dry ashing with wet ashing, and then ash it again. Some carbon matter or organic matter is really hard to oxidize or to burn off, so sometimes you need to do that. the more white your ash is or lighter in color, that means you got rid of most of your organics. And you have mostly your minerals there. Minerals or any contaminants like sand contaminants, soil contaminants, they won't burn off. Anyway, so that ash material is mostly your starting material. And white ashing is a different type of preparation where you actually put a combination of concentrated acids and digest your sample. So instead of burning it at really high temperature, around 470 to 550 degrees Celsius, you actually digest it somewhere between 200 to 250 degrees Celsius with concentrated acid. So again, here you are burning off your organic. Again, your organic matter oxidizes into carbon dioxide, sulfur, SO2, sulfuric, SO2, sulfur dioxide, and then NO2. So everything gets oxidized, and then what is left in your acid is your mineral elements. Very rarely there's a direct injection where you don't need to ash your sample, like oil or water. You're looking at mineral content in oil or water. You don't need to ash your sample. So here in this box, I bring your attention to reagents, blanks, standards, and glassware. So sometimes your reagents are contaminated with minerals. So what happens is you run a blank. So the way you prepare your sample, you prepare a blank without your sample and use the same reagent. So the blank corrects for any contamination that comes from reagents. Sometimes your glassware is contaminated from previous use. So all of the glassware for this lab is washed, acid washed. So your crucibles are acid washed and ashed without your sample so that there's nothing in there from previous run. All of the glassware that you use is acid washed to prevent any contamination. So this lab requires a lot of preparation. So Cindy and the TAs put a lot of effort to make sure that your experiment works. So all of the glassware are acid washed so that we don't have contamination from labware, and we run a blank to make sure that accounts for any contamination from reagents. Standards are important because we need standards to calibrate so that you can detect concentration or measure concentration in your unknown samples. So standards are usually very pure, 99.99% purity, and we again run standards ahead of time to determine linearity. You want to make sure that you have a linear standard curve. Therefore, every element requires different concentration to get that linear portion of the curve, okay? So that we can apply the linear equation of the line to do our prediction of the concentration, okay? So we do that, and we determine the dilution that is necessary to get within our linear range. You don't want to be outside of the prediction linear range because that will cause another error. So that could cause an over or even an underestimation depending on the standard curve that you have. So let's say in the lab you over diluted or did not dilute adequately. If your sample is concentrated, it might fall outside of the standard curve, either below or over. In this case, you are not accurately measuring your concentration. So it has to be within that standard curve range. Okay. Interferences that causes over or underestimation. This is important for your lab report question 4. So sometimes you have, this is what I mentioned earlier about spectral interferences. So you have elements that absorb light in very similar ranges. So for example, iron and zinc absorb light. Their maximum absorption are very close in terms of their wavelength, that maximum absorption or lambda max. So in this case, you try to choose a wavelength that does not overlap with the other one. Although it could not be lambda max, could be another wavelength, but you can still measure absorption, so you select that wavelength. And you again play around with your slit width. Background. So we talked about this a little bit when you have incomplete atomization. If your mineral or your flame is too cold or not hot enough, that means you don't get atomization. Your molecule is there and it's kind of big molecule, so it scatters light. So you get less light that reaches the detector. It will be misinterpreted as higher absorption and overestimation, when in fact it's just you didn't get complete atomization. Transport interferences. So that means if your reagents that you're using or your sample, in whatever is in the ash material, you have other interferences that absorb at the same wavelength or similar wavelength. So we try to prepare the standards the same way as the sample, but sometimes this is not avoidable if you have lots of interferences from the matrix. So that is why proper ashing is really important in this case, so that you can release your minerals from the carbon matter, so that you don't have interferences from organics in your sample analysis. Solute volatilization, that is potentially a problem when you have a mineral that can form large molecules. So example here, you have calcium can form large molecule with phosphorus, can form calcium pyrophosphate, which is a large molecule. So calcium can bind with phosphate, and then phosphate can bind with multiple calcium. So you end up with a large molecule with a lot of calcium, a lot of phosphorus. We call that calcium pyrophosphate. So this would not really get into your mist that gets volatilized into the flame. So that would cause underestimation. And that's what most of you did already in the lab. You added lanthanum chloride. And lanthanum replaces calcium in the phosphate molecule. So lanthanum replaces calcium, and then calcium becomes more soluble and present to be volatilized. Ionization can happen, and we talked about the fact that ionization is not something you want to do, especially you control the flame temperature. So you control the flame to be not too hot so that you don't get the atoms ionizing. Because then the ions will not absorb at the same wavelength that you've selected for the atom. So you get underestimation in this case. Okay? So other, not necessarily interference, another reason for underestimation is your volatile elements. So if you have iron and zinc, these are volatiles. So during the ashing, we have to be really careful not to induce volatilization of volatile elements, because iron is very volatile, and if you get an underestimation, one of the reasons for underestimation is loss of iron during ashing. And that happens more in dry ashing versus wet ashing. Because in wet ashing, you use much lower temperature, so you prevent volatilization of iron in wet ashing more than you can in dry ashing. Okay. Last bit here for the atomic absorption is a comparison of atomic absorption versus ICP atomic emission. So both are great in measuring trace elements, and they have excellent precision and accuracy. So both are really good in that regard. One advantage of atomic absorption spectroscopy over ICP is that an older technique has been figured out. All of the troubleshooting has been figured out for that, just since it's an older technique. And you have wide availability of the instrument. It's cheaper than the ICP. But with ICP, you don't need a lab, so multiple elements can be run or detected in a single run, especially if you have the Echelle detector where many elements can be run at the same time. So that makes it high throughput, more efficient, you can get more out of it. And your atoms or elements are stable at high temperature. They don't get ionized, even though the temperature is really high. The other advantage for ICP is detection limit. So you really can detect at very low concentration compared to atomic absorption. So you can look at table 9.5 in your chapter to look at the differences in detection limits. That's it for atomic absorption. You guys are done.